Rhino. First, I will show you the Human by Design exhibition tables. It's the one that you requested. It was also planned to do that. We can have a better look here. So we'll try to somehow simplify a little bit the process here. What happened with the Voronoi, then what happened with the undulated surface, the isocurves. I will show you how to turn that into something that is a furniture, and also we'll make a simplified version of this, like a very, very simplified version of this. So this is my Rhino pin. So I'm always opening Grasshopper as a first thing, but in fact here we should start with something else first. Maybe we should make some sort of a landscape, some undulated landscape. So instead of using Grasshopper immediately, I will draw some surface here. When I want to make something that is curved or wavy, I first start with a flat surface like this one, then rebuild to get more control points. So like 5 times 5 is okay. Now let's do it like this. I will switch on the chat. Whenever you want to ask me something, just please do so. Okay, I see the chat now. Okay. So I will make a surface that looks a little bit more wavy, like this. I'm pulling all the points upwards because that's the top of the table. So we don't want the top of the table to be underground. So maybe something like this. And also the center, just a little bit. Okay. And I will move the whole thing a little bit upwards because we also don't want the tables to be way too short. So this is something that I will reference to Grasshopper like this. So surface, set one surface, bifocals. You know, I don't understand the icons. I need to have I need to see the names. So now I will project. No, I want to populate the ground underneath this curved surface with points, with random points. So first I will just create some sort of a bounding box like this. So there is a bounding box that contains this surface. I will populate that bounding box with random points like this. I need the random points to actually generate the Voronoi. Do you know the concept of the Voronoi diagram? No. Okay. I'm just looking for an article that was published by a new media artist. I just forgot who was it. A Voronoi diagram is something that looks like this. I will show you pictures. So it's something like this, where you can see that there is a point, like there is a lot of green points here, and then there are some polygons, some areas, and the areas are actually the most fair area that should belong to the point. In fact, you can imagine that each one of these cells is a bubble, and if the bubble is really small around the green dot, it's just a circle, and when it starts growing, at a certain point, it hits some other bubble, and they will create this straight line. So it actually works like that. If you had a soap bubble foam, and if you cut it, you will see the Voronoi diagram. The same happens for the giraffe. It's got a Voronoi pattern on on the fur, on the skin. Also, when the soil is drying out, it's basically drying out in the Voronoi diagram shape, because the distribution of the areas is the most fair one. And it all matters on the distribution of the random central points. So if the central points are distributed evenly in some pattern, also the Voronoi will be regular and will follow some pattern. But if not, then it looks something like that we have here. And you can see that there's a lot of applications of this principle in art and architecture. And the article that I was looking for was somebody was calling for forbidding the Voronoi diagram for at least 10 years, or maybe it was 6 years, but it was more than 10 years ago, so now it's not forbidden anymore. But if you overuse it in Grasshopper, it tells you that you should stop using it, and it shows you like, I will show you a warning that it's not a good idea to overuse Voronoi because it's not good for you. Where is it?
May I ask a question?
Yes.
Why is the forbidden? Is that?
It's kind of a joke, but this is when you overuse the Voronoi diagram in Grasshopper. It tells you something like this: excessive use of Voronoi diagrams has been associated with, you know, it has been overused by architects and artists for sure. And it's such an easy thing. It's one-click solution, and you make one click and you're done. It actually gives you a result. And that's one thing that I was talking about when I was talking about the overuse of plugins for Grasshopper. I think that some of the plugins, they just offer an out-of-the-box design solution. So basically, they give you a design in one click. And Voronoi is one of those. And many people actually overuse the Voronoi diagram for this purpose. And so did we actually, to be honest. This is a complete like overuse or use of Voronoi diagram, but then it makes a lot of sense in this situation because we really needed to parcellate the landscape into elements that have their own fair share of the real estate ground. And yeah, it made a lot of sense here. And we did a lot of work on top of that Voronoi. Unlike when you Google for that, you see that all the things that you see here are just one-click things. There is no added effort into what you see here. Anyway, so that was kind of a joke that you shouldn't be using that. So to actually generate a Voronoi diagram, it can be three-dimensional. We care about the two-dimensional version. We need to have some random points that are on the same level. So I will project these points onto the ground plane, which is here. So let's just make sure that we are projecting it to the XY plane. So we don't care about this anymore. I will hide it. So I care about this only, all these points down here. And I can create a Voronoi diagram based on this, but I also want to trim the excessive ones. So I will also project the surface itself on the ground. And then I want to know if the point is inside of the surface or not. So I believe it's here, or maybe an intersection point in, let's see. Point in curve. We can consider this to be a curve. It automatically casts or converts the shape, the surface, into a curve that is its circumference, and that's the curve, and these are the points, and it tells me if it's inside or not. So the result, the answer, is here, and there are three options: either outside, which is 0, or inside, which is 1. On the edge, which is 1, or inside, which is 2. So in Grasshopper, when you are asking about you can convert many values to many types to different types. So one type that you can convert is a number, and you can convert it into a Boolean. Boolean is basically only true or false. And the conversion goes 0 is converted to false. Anything else is converted to true. So if I convert this to a Boolean like this, if I use a container called Boolean, whatever I insert it tries to convert it to Boolean. On the output, I've got values that are true or false. And whatever was 0 is false. Whatever was not 0 is true. And for me, this is good because I only care about those that are either 1 or 2, which means either on the edge or outside or inside. So this gives me a good pattern. I can do cal pattern, which basically leaves only those that in the pattern are true. So like this now only the points that are inside remained. I will just hide this again. Also this. So now I have points that are inside, and I can apply the Voronoi diagram now, which is kind of forbidden, but it's this one. So it requires the points. I believe it's the first one, yes. And it generates the Voronoi diagram for you. You can also plug in the boundary. Out of the curiosity, if I say this, okay, that's good. If I say this, it doesn't work. Okay, I can use the box as the boundary. It makes the projection of the box on the ground, and that can be used as a boundary. So yeah, this works well. So let's keep it this way. Now I've got some Voronoi cells here that are around the points. That's useful. I will also hide the surface for the moment. Let's focus on the Voronoi cells. The Voronoi cells are actually polyline curves. So each one of them is like a closed curve. I will bake them to show you. Now it's baked, and I can select either this one or this one or this one and this one. You see, so they are closed polygons, which is good. That's kind of useful. But I still will need the points, the original points. And I will do this. I will pull. No, that wouldn't work. What I want to achieve is this. This is the surface. There are some points underneath. And I want to somehow design all the tables by lifting the Voronoi diagram upwards until it touches the surface, and then I want to adjust its orientation to be tangent to the surface. And that can be done quite easily. I will show you the wrong way, and then we'll fix that wrong way. There is something called pull or surface brep, surface closest point. So I've got a surface, which is this one. I will plug it here. I've got all the points, which is this. I will plug it here. And it basically tells me what is the closest point to my point to the source. This is the source point. And it finds the closest point on the surface. And it tells me what is the position of the closest point, and also what is the UV coordinate, which is a local coordinate on the surface. You can imagine that the surface has its own coordinates, just like the domains of the lines. The domains of the surface are two-dimensional. So 0, 0 would be here, 1, 1 would be here. The center will be 0.5, 0.5. And you can just like define any point on the surface by the local coordinates, which is called UV point. And at that UV point, you can do some more analysis. For example, you can evaluate surface like this. So first you need to have the surface, which is the one that we have. And then you specify a UV point on the surface, which are these. And it tells you what is the point there. We know that already. What is the normal, which is a vector perpendicular to the point, to the surface at that point, which is super important here. It tells you the position. So yeah, the U and V coordinate, that doesn't matter so much, and then the frame, which is basically a plane that is tangent to the surface at that point. So let's see how does it actually look. So it's this, and they are super small because I changed it yesterday to make it really small. So I'll make it bigger. This is too much, so let's make it like this. Okay, now you see this distributed some planes so that they are tangent to the, they are copying the angle of that surface. The problem here is that these are the surface closest points. These are the original points. And when I draw a line between them, between the bottom and the top points, you see that these are not horizontal because, I mean vertical, because surprisingly, this point was the closest point to this point, and it's not the one that would be completely vertically above. So we can do two things. If there is a possibility to project on surface, then that would be actually cool. No, there is no possibility to do that. But what we can do is we can actually draw a vertical line, then find an intersection between the surface and the vertical line, and that is the point that we care about. So instead of just finding the closest point, let's just draw a vertical line, which is the easiest way is line SDL, which means line, start, direction, and length. So this is the start of the line. Direction is a z vector, which means the vertical vector upwards. And the length should be something like a large number. So right now it's 1, so let's make it 100. So we have really long vertical lines. So these are the lines that I'm drawing, and all of them are intersecting the surface, which is good. And now let's find the physical intersection between these lines and the surface. So so it's not line surface, but line B rep. It can be B rep. Yeah, B rep. B rep is the grasshopper name for polysurface, which means a surface that consists of more surfaces, just like a cylinder, for example. It's made of the outer surface, top surface, and bottom surface. So there are 3 surfaces in that B rep. A B rep stands for boundary representative. So a cube would be 6 surfaces, a polysurface made of 6 surfaces, and so on. But even a single surface is actually a B rep consisting of 1 surface. So we are looking for an intersection between a B rep, which is this surface, and these lines. Also, I think there is a bug in Grasshopper. Let's see. Maybe it's fixed meanwhile, but let's see. If not, then flatten. Okay, it's fixed. So we can keep it this way. You see that it graphed it to make it into a data tree. I'm not really going to explain data trees. I somehow expect you to already know it. If not, it's in the essential bundle that I gave to you, so you can learn that. But I will just, I'm just going to use the data trees here. The data tree, that this component actually grafts, because it can graft, it means that each line can possibly intersect with the surface more than once. If the surface was something like a C shape, you can imagine that the line actually intersects the surface more than once. So for each branch, we've got all the point intersections of that specific line with the surface. So instead of flattening here, I will rather graft the original list of points. Now each point is contained in its own separate branch. And if I draw a line like this, then basically the first branch matches with the first branch here, and it draws a line that goes from the bottom point to the top point. I will just double check if it actually works. Yes, it seems like all the lines are now touching the surface. This is only to check whether this point is actually the right point that I need. And the rest we already have. Now I'm going to find the closest point to this point, but actually it will very probably be the point itself. But this component gives me the UV coordinates that I need. And then this component evaluates the surface at that point. So you can see that now I've got an evaluation, the frame of the surface right above the original point down here. So I've got a vertical line and then I've got a plane there. And you already see that this kind of looks like a table already. What am I going to do is this. I'm going to take the Voronoi that is here. Each one of these points now has its own Voronoi cell. I will graft the Voronoi cells just like I grafted these. And now I can show you what can you do with the Voronoi cells. You can actually rebuild the curve. The Voronoi cell is a polyline. And I can rebuild the curve to not to be a polyline, but to be something smoother. Actually, this is not the best way of doing it. I will just take control points of the Voronoi cells, which basically are just the corner points. And I will use these points to actually draw Nurbs curve, which is this curve. Like this one. I will make it periodic. I will close it so that there is no angle here. So toggle like this. Oh yeah, the reason this is so sharp is that there is actually this Voronoi cell starts here with a point, then goes here, 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 and there is again the same point as the last point. So we can actually cull index, which means we are getting rid of the first point in the row because that one is there twice. And if I do this, it should work. And actually, it doesn't really look much better, but that's right. Oh yeah, it doesn't look much better here because there are 2 points very close to each other. So of course, it doesn't look so good. But anyway, you see that I changed the original heart shape, this one, into something that is much smoother. And this is what we have done here as well. So if you look at the bottoms of the tables, they are smooth, but the tops are not smooth. I will come to that just shortly. I can scale this down also, but there is no need. So now we are sure that these pebble-like structures, they can sit next to each other and they don't interfere. They don't really make any mess. So now we've got the bottom plate. Let's make the top plate, which is super simple. I will take all these polygons and I will project them to these planes up here. I could have oriented that, but imagine that something was very vertical. So I would just take that and just put it vertical like this. Instead, I want to take it and project it so that the top view is one above another, so that there is no, like they look the same if you look from above. That's because I don't want to lose any real estate. This will save a lot of real estate. So I will go project onto a plane. So I will take the original cells. This is the geometry, and I will project them on the planes. And you see that now when, at least I hope so, when I look from above, let's see from the top view, maybe I need to project on a vector, project along, yes, direction, yes. So I need to take the geometry, projection, plane, and direction, which is going to be z vector, so vertical. And now you see that it looks the same from above, but if we look into perspective, then you see that this is actually, you see it's in the space. So it's copying the shape of the surface. They don't fit perfectly, of course, because the surface is continuous and we are aligning the board or the polygon to just the center of the Voronoi cell, and it remains flat. All of them, they can be made of wood, so they are flat. Okay, and then I will make it a little bit smoother, just like we did here. So you see that they have filleted edges. So I will do the same here, and it's called fillet. Hopefully that works because we've got some really small kinks. And let's set the radius to something. Right now it's nothing, so I will do 1.5, for example. And let's see what does it do. I can change the slider and it makes the corners smoother and smoother. So that works for me. I think that's really nice. But you see that at some points it doesn't work so much because the corner there is too small, like here, for example. So it doesn't really, you know, originally it's so close, it cannot be done any smoother. So let's make it as smooth as possible, like this, or maybe even more than 10. I will just make it 15. Yeah, that looks good. Even this is kind of funny. So I've got top plates, I've got bottom plates, and they somehow belong to each other. The good thing is that thanks to the tree structure, now when you look what is inside of the data tree, I will simplify here to get rid of unnecessary. Oh, that wasn't simplify. This is simplify. So I will get rid of unnecessary zeros in the path. So now I've got 71 branches. Each one contains one bottom piece. And here I've got 71 branches. Simplify again. Each one contains one of the top boards, which is pretty cool. I can use this to actually generate the bottom and the top plate of each of the tables. So this is the start, and now we should actually have a look at the legs. So far so good. Is it understandable? All good? I will just check my Facebook. Yeah, it doesn't seem anybody has commented. That's good. Yes means all good, no questions. Is that the yes? Okay, I hope. Okay, good. So let's play with the legs. And I told you we kind of used some sort of a brute force because I think there is no reason not to, and I will explain why. So now I will show you how did we generate those 5,500 versions of the table and picked just one for each one. Maybe we can do something. Yeah. Let's start with just one. Now we've got a lot of tables here, 71 tables here. Let's just pick one. Let's just pick the first one. So I will flatten here. We'll come back here and change it afterwards. But I will flatten that to get actually just a flat list. Then I will take the first item like this and this. So now we are going to work on this table. So this is the bottom, this is the top. I can actually hide the top surface because it's an obstacle. So it's in layer default. I will just switch off layer default, but it still works. It's still referenced to Grasshopper, so I don't have to worry. I just don't want to see it. And now I've got these two. So now how can I actually create those legs? Well, the leg has to be flat. And the leg also, what is given here, it has a fixed length here and a fixed length here. In fact, this was 7 centimeters, this was 5 centimeters, and it applied to every single one of them, no matter how long it was. Always the bottom edge was 7 centimeters, the top edge was 5 centimeters. So I need to somehow create some edges. And the easiest thing would be to actually have some plane. So and cut these things with a plane. So let's make the plane first. So I will take the bottom plate. I will find the central point of that bottom plate, which is the easiest way is to ask for an area like this. A side effect of the area measurement is the central point, which is this one. And I can place some sort of a vertical plane there. And let's use the XZ plane just as a test. So it's a plane that looks like this, and I will set its origin to the center of my table like this. And then I will make intersection between that plane and those two curves. So actually, the easiest thing is to look it up because I don't know how is it actually called, but it should be curve. No, it should be plane curve, this one. So the curve that I want to intersect is this one. Actually, let's make it a little bit more visible. Like this. This is curve. So this is the bottom curve. I will do it like this. Nope. Nope. What's wrong? It's the bifocals. Okay. Okay, it's the bottom curve. Oh, this should be the top curve. Like that. So this is the plane, and it actually, this is an intersection between this plane, and this curve, and the intersection is here and here. So I've got 2 points here. Let's draw a line between them. I'm thinking, what is the best thing to do? Yeah, let's draw a line and see. Actually, I can draw a polyline because now this is a list of points, and if I use a list of points here, it actually draws a line. So the bottom edge of the leg should be on this line somewhere, and I should pick a random position for the leg, and I will do it. How will I do it? Now I'm thinking I should pick a random point on the curve and then draw 7 centimeters long line, which means, okay, which means that I will reparameterize this curve to make sure that its domain is between 0 and 1. And then I will generate a random number between 0 and 1. Also, the random seed can be anything. So I will change the random seed like this and evaluate the curve like this. So this is the curve that I'm evaluating. This is the parameter. So now you see that I found a point here, and I will draw a line that is 7 centimeters long, or actually I don't know how much long, but because I'm in a different scale. So let's say 3 units, 3 millimeters. That is my scale here. So I will draw line SDL, start, direction, length. From this point, I will specify the direction a little bit later, and I will say it should be 3 units long. And the direction should be actually a vector from the first line to the second line. So basically, I will take these from the first point to the second point, of course. So I will take this. Those are the 2 points, first point and second point. And this is the first point, second point. I will create a vector from one point to another. For those of you who know, I could have done it easier like this, but I just don't like to be that implicit. So basically, a straight line can convert to a vector basically by defining the vector from the start point to the end point of the line. But that's way too implicit. This is way more explicit. This is way more clear. What am I doing? So this is the direction of the line. And you see now I've got 3 millimeters long line that is part of the curve that the line that I defined here. So basically that's the bottom edge of the leg. The problem is that if this random actually just randomly jumps outside, like if it's way too close to the edge, it could happen that the line will be outside of that curve, like here, you see, because I'm not checking where am I. So in fact, before I evaluate the curve at the random point, I need to make sure that it's 3 units shorter than it was at the end. To actually, I will chop off the last 3 millimeters, so that the random start of that leg should happen anywhere between here and 3 millimeters from the end. And if it actually jumps to the end, it actually reaches the very end. So I need to make sure that the curve is shorter, and I think I can use extend curve component. Let's see. And it actually makes the curve longer at the beginning and at the end. But I can actually probably say that at the end, it should be shorter if I set negative number. So if this is the length, I will set the negative number here and 0 here, and I hope it actually makes the curve shorter than it was. And it seems like it works. Yes, now this is 3 units shorter, so I'm absolutely sure that, actually I will plug it here like this and here because I'm reparametrizing here. So I'm absolutely sure that the bottom edge of the leg certainly remains inside of that curve, this one. Then I do the very same thing for the top curve, but I will have to chop it with the same plane. The reason is that I want the bottom edge and the top edge to be on the same plane so that the leg is made of a flat material. So I'm chopping the top curve with the same vertical plane, and I end up having some line here, some line here. The thing is that I should change the random value here. And now if I connect these two lines with, for example, a loft, like this. Loft is a surface that is defined by its sections. So I've got 2 sections of the loft, and this is the result. I see that I need to flip one of those lines. Flip curve, this one. This might be a problem because that's kind of a random thing. So now I've got one of the legs. So you see that this is a valid leg. The thing is that I need to generate more of them, and I will do it in a loop. But before, I just want to generate more layers by which I'm cutting the more planes that can contain the legs. So now I'm using the XZ plane, but instead I want to make something random. So I'm not only allowing the plane to be in the center, but also I will allow it to be anywhere on the surface. So or on this bottom surface. So basically, I can just say that I want to populate a surface with points, which is populate geometry, I believe. But if I do that, it probably only puts points on the edge. Well, yes, it did. So before I do that, I will convert this curve into a surface, which is boundary surface, like this. That's my geometry, and I populated it, and it gave me 100 random points. And I can use that as the origin of my vertical plane. And probably at the end, I will end up having a lot of different legs here. That's true. Some of them, the problem is that you can never know where is the beginning and where is the end of a section line. So sometimes it's flipped, it's connecting, like this is the first point, second point, third point, fourth point. That's why it looks like a butterfly. Here, it's 1, 2, 3, 4. So it doesn't look like a butterfly. But let's not fix this issue because that's way more complicated and it took me a while to actually fix it to make sure that every time it works well. But anyway, this gave me 100 legs. They are all parallel because all the cutting planes are parallel. They only start on different locations. So not only I need to make it less parallel, but in a different location, but I also need to rotate it somehow. So let's keep that. No, it doesn't have to be vertical. I can rotate around what? Rotate 3D. That's what I want to do. So I will start with a plane, which is all of these planes. They are basically the same plane, just placed in a different location. And then that's the geometry that I want to rotate. The angle I will specify later. The center of the rotation is the center of the plane. That's okay. The axis of the rotation can be something random. So any line can be the axis of the rotation. I will just generate, well, it should be a line. It's not a vector. No, it is a vector. So we need to define a random vector. Despite what I told you, I'm going to use the random vector from my Boyd library. And I also want to generate as many as I have these random points. So if they are 50, for example, this is 50 random points, then I want to have 50 random vectors, that's the axis. And also I want to have 50 random angles. And now you see that this is randomly rotated somehow, but then eventually, oh, I'm not really using them yet, but I will just use the randomly rotated planes to actually generate the sections. And well, it doesn't work. The reason why it doesn't work is that sometimes it gives you a section. Sometimes the plane does make a section of the bottom and top curve, and sometimes it does not. And we only care about those cases where it cuts both the bottom and the top plane. So I need to make sure that there are 2 points here and also 2 points here each time that I'm evaluating. So I will just request the length of the list length, list length. So this gives me an answer for every single branch, how many items is contained in the branch. And I want to make sure it is equal to 2. I need exactly 2 points here. And I also need exactly 2 points down here. So if both of these cases are true, which is a logical AND gate, like if this is true and this is true, then I want to keep that. Then I want to keep that couple. So it gives me a lot of true-false statements. And because I'm working with a data tree, this is a little bit more complicated. So I think I'll try to do it this way. Call pattern, list pattern. Okay. If this works, then it's kind of easy, but I'm afraid it wouldn't. So this contains now 54 units. 54, yeah, this could work. So now this only contains those values that, yeah, only those branches that contain 2 points do actually contain something. So the other ones are just empty, and I will just reuse those. So I got rid of those possible sections that didn't contain 2 points on top and 2 points on bottom. And also what I can do is before I move on, I can do clean three like this one, and that removes branches that contain nothing. I just need to switch it on here. This removes branches that contain nothing. I'll plug it here, and the same for the other one. So this will be pruned 3, And hopefully now it works. Okay, so only those legs that actually work well, only those remained. And that's 54 legs, 27 legs only. Okay. And I want to somehow select some of these legs that don't intersect. And this is kind of a problem because you know, it's all about in which order you place these legs. And if you place them in the correct order, maybe they, like, you could place more of them than if you place them in wrong order. So now this is kind of a complicated thing. You know what? I've forgotten to save, so I'm going to save Digital Futures. Yeah, I'm just placing it all here. D5 file 01. Okay. So now I need to pick only those that don't intersect. So instead of doing like much more work, I actually can add more here. Okay, so let's generate more of these legs. Now there 48 legs remained. The other ones, they didn't make a section of both of these bottom and top. And I need to select 5 of these legs so that they don't intersect. So what can I do? I can, let's do it the brute force. I will flatten here, flatten here. So now I've got a list of 48 surfaces that can become legs. The next thing is that I want to keep adding legs one by one. And if one of them actually intersects, then I'm not going to use it. Yeah, I will show you. So let's start anemone. Let's start the loop like this. And again, I need to have a pool of possible legs from which I'm going to choose, and a pool and a pool of already used legs that remained. So I'm going to pick one. We need to start with one. So I'm going to take list item from here. This is the first leg. And I'm also going to use the first leg as the first one that I've chosen. And then I want to also remove it from all the possible second legs. So I will call index. And the index is also 0. So I'm picking leg number 0 and removing leg number 0. So this is leg number 0, and this is all the other legs that are not number 0. So in the loop, I want to have 2 loopback data. One is the leg 0. The other one are all the other legs. So you know what? I actually want to do this. No, that's good. That's good. Let's do it like this. I want to do it again, though. So no, not really. I don't want to do it again. I want to measure whether all the other ones, I want to keep only those legs that don't intersect with this one. So I care about the intersection of each one of these with the one that I already have. So let's see what sort of intersections can I make. I believe it's a BREP intersection, which is this one. Also, it could be just a surface, but I don't think there is a surface. There is a BREP. What about here? No, it's BREP like this. As I told you, a surface can be considered a BREP. So I think maybe I will switch off the parallel computing here because one of these parallel components is broken. I forgot which one. So I just right click and switch off parallel computing because it's faster, but it's broken and it causes a problem. So I'm checking whether the one leg that I already have intersects with all the other ones. And the answer is like this. So I should have 47 branches, and only one of them actually intersects. And we can even see it here. Just one of the legs intersects my leg, which actually is a good thing. So here, this one intersects, and that's the one that I want to get rid of. So let's measure the length of the list here. So if this intersection contains something, if it's not 0, if it's anything else but 0 here, then I want to get rid of it. So I will convert it to Boolean again. And as you know, whatever was 0 is going to be false, whatever is 1 is going to be true. But if I use the cal component, cal pattern, if I want to remove from the list all that intersect, then cal is not good, because this only removes, wait. Okay, I need to flatten again, or maybe, yeah, flatten, so that they are all in the same shape. And you see that instead of removing the one that intersects, it kept the one because that was the only one that was marked true. So what I need to do is I need to use gate not, which changes true to false and false to true. It's a logical not operator. And now the pattern is negative to that. And now these are all the legs that can be the second leg in the collection. And I need to pick one of them to be the next one, because the first one is already chosen. And then I need to pick another one, the second one. So out of these, I can pick a random leg. I can use, no, let's pick a random number. So I need to know from how many am I choosing. So this is a list length. It says 46. Then I do random. This gives me a random number between 0 and 46, which is an index for a list item. And I will pick one that I will randomly pick one, which could be this one, and that could be the one that I can add to the collection. So these two, they work fine together. The thing is that this has to be a little bit more complicated, because I need to clean up all the lists properly. The only problem is that we don't have that much time. So for the rest of the definition, I may finish it during the second tutorial that Tomáš will make, but I will explain to you what is going to happen next, and I will send you the finished file afterwards, because when I'm also explaining and doing stuff, we wouldn't manage to finish on time. So basically, now I've got two legs, and in the next iteration, in the next step of the loop, I will do the same. I will check all the possible third legs, remove those that intersect with the already selected legs. Out of the remaining ones, I will pick one and add it to the collection, and I will do this 5 times. And I hope that I will find 5 legs that don't intersect each other, and maybe I will find less. When I'm done, I've got a solution for that one table, which is, wait, where is the table? No, that's not the table. So I've got one solution for this table. And then, because I'm using a lot of randomness here, that I can do the same operation, like the same procedure again, with different random seeds. So I will have a different first leg, then therefore I will have a different random second leg, and so on. So I will probably select more different legs, and I can repeat this as many times as I want. So I can eventually have like 100 different combinations of 5 legs for this table. And then I can pick from those simply by measuring the distance between the top edges, like from here to here, and then to the second, and so on. And if the overall distance here and the overall distance here is the largest of all the selected versions of the table, then it's probably the best solution, because it means that the distribution of the legs is the most even one, like it's distributed all over the table the best. So I will pick that solution, which will be the best, the stiffest solution for that table. And I can do that for the next table. I've got 71 of these tables. And if you imagine, this actually gives you a lot of combinations. Most of them are random, but still they follow certain rules, and it gives you a good control over the result. All right, I will just quietly finish this definition, and then so that I can send it to you. Meanwhile, I would ask Tomáš to get ready for his tutorial. And yes, of course, you can ask questions. I'm going to read it, or maybe you can ask me directly. But the question about the exhibition, I didn't understand in the project base on what the first surface emerged. Oh, okay, that thing. So that first surface, this one, yes, that was mainly, it was a combination. If you look at that space here, we knew that, you know, like for example, here, there is a corner and these are actually shopping windows. And we know that here we need something that is opening up to the center. So we knew, so we manually adjusted the surface so that you pull the surface upwards. And we knew that it's going to do something like this. So we manually pulled the surface so that it's actually rotated inwards. Then we knew that we want something emerge here in the middle, and we didn't really care much what it is and how does it look. So we slightly pulled it up. Then there is a wall here, and we knew that we want that to actually climb the wall and so on. And also for some of these exhibits, we knew that we are exhibiting something tall, so the platform should be short, or we want to exhibit something that is very tiny and it has to be really high, close to your eyes. So we also made some automatic adjustments based on the size and position that each of the exhibits requires. Was that a good answer? Okay. So any other question? I will check the Facebook. Maybe there is some question. All good. Somebody is crying over our video. That's not a good sign. Okay. So now it's time for Tomáš. I will stop sharing my screen and do you want to make a 5 minutes break, or can we continue immediately? I think join. The answer is both works. So yeah, we can see your knee. We can see your knee. Not anymore. It's an okay knee. No. We can hear you now.
Okay, great. Hi guys. Okay, now share screen. And let's make it green. Just a minute and I'll be all set up. Okay, until everything starts, just please Chat. Everything's fine, yeah? Or you can see my screen and you can hear me and everything works, right? Okay, great. So I will be explaining you very briefly how this force field project begin. What's the grasshopper behind it? What's the process, and what are the limits that you have to have in mind when you actually want to achieve something like this being fabricated? That's maybe the most important and interesting thing when doing these projects, that we are all the time prototyping, all the time going between fabrication, material, and then checking out all the material and fabrication limitations and incorporating them into the process, into the Grasshopper script. Yeah, let's have a quick look on the structure. So basically, you can see that it's it started as a grid of elements. So we have these scales, these little steel cards that are aligning according to some gradients. They are placed somewhere in a space, and and they have certain orientations. Here in the visualizations, you can see also different angles, and in the scheme over here, you can see basically what was the idea behind how the pieces should lock one to another, and how they are actually placed and held tightly with a basic steel rod. So let's go to Rhino and let's start. As I said, we started with a grid of points. So let's have that. It's either rectangular or square grid. I will use rectangular because maybe we will have to adjust the scale in every direction differently. Size of the cells and number of cells. So we will use 2 sliders for each of these inputs. Let's have it like this. We doesn't really need to change the scale, but I like to work not so small scale, because I don't like to see the basic Rhino grid. So I will scale it up a little. Let's have it like 20 by 20, or maybe let's make it 40 by 20. Okay. Next step was next step was that we need, instead of cells, we need the representation of position of each of the scale. That is represented by center point of these grid cells. So let's see. Okay, the data we have here is aligned and is we have 22 branches with 25. Okay, yeah, 22 branches with 25 items. That means that on 3 branches of this data tree, we have as an output, we are having columns, and as a list on each of the data tree, we have we have the cells themselves, like a rectangle cells. To get the representation of point instead of cell, we have to somehow use certain components. For example, one of the way is to use area component, which measures the area of each of the cell, but also it gives us the centroid. The data structure is still the same as it was, so we can rely that on certain branches we have columns, and on lists of those branches we have lines. This will be why I'm speaking about these columns and lines is because when I go back here to the input pictures, you can see, not here in the visualization, but in the prototype we have made, that we go somehow zigzag. The first column of these scales are, the centers are located, can I actually draw here? Like this. No. Are located on certain elements, and then the column next to it is in between them. Then the next one is on this location. So basically, what I wanted to achieve is to have something, to have points aligned in a structure as a chessboard, basically. Let's at first take a look onto the data structure. So three statistics. With the three statistics component, you can see what are the paths to the branches of the tree. Now we can use list item to select this path, a certain path of the list of the paths, and then with tree branch component we can pick only one of them. So you can see here that when I am displaying these data we have here, that on a 0 position, that means 0, 0, 0 branch of the data tree, there is, when I'm highlighting, is this the first column of our data. When I use a slider to scroll through the items, you can see that I am scrolling over the columns of the grid. Now I need to pick even numbers and treat them like keeping the first, the third, and the fifth, and so on points. And with the odd columns, I need to do the inverted logic. So let's divide our data like this. As an output of three statistics, we get the list of tree branch addresses, and we can treat this as a regular data stream. So we can, using this patch, we can divide them into A list and B list according to certain pattern. The pattern over here is true false. That means we take the first item and treat it by the true value. That means it will go to the A output. and the second item to read it with false value, that means it goes through the B output. Since we have the pattern we don't have the pattern defined by more items, only with these two, we will repeat this true false up till the end of the data list. So that means that at the output I get the odd and the even columns or even branches of the data tree. And here, instead of listing just one item and selecting branch with 3 branch component, I can use, I'll delete this, I can use 2 branches, select first part with the A output and the second part with the B output. The great thing about Grasshopper data treatment is that I still keep the addresses of data tree, so we can treat these branches a way we want or a way we need, and then we can put them together and reassemble the data structure we had. So this is a great thing about data trees and the Grasshopper working with data. This is maybe a little more advanced thing to do with Grasshopper, this data management, but I believe this is the basic knowledge you need to have when you want to go one step further from the basic definitions, basic thinking of how to work with parametric design in Grasshopper. So first part of columns, second part of the columns. Now we need to, in a very similar logic, select and keep only every second every other item of these points. So for that we can just call the list, and we can call it by the pattern we can set by hand, or this would be better idea, we use merge. And the pattern for calling, or basically always working in Grasshopper, when we are working with patterns, we can use either zeros and ones, zeros meaning false, ones meaning true, or we can use true and false values. It doesn't matter. We can show actually both of the ways. So for the first, I'm using Boolean toggle. These buttons, and I can set it first to true, second to false. I have these two values over here, and I can use this this pattern I created for calling the items from a list. This will be the list I want to call. So as the output, I get every second item. I keep actually the item which has true value. I'm numbering from this lower left corner, so that means true is the first one, false is the second one, and so on up till the end of the column. So true, false, true, false. For doing the same thing on the second set of the columns, I will do the inverted pattern, and I will keep only odd numbers. So the same call pattern, but I need to create another one which is inverted, and that I will just show you. We can do merge, and we can use panel for drawing or for creating number 0. And number 1. Now true is 1, false is 0. Now I need to do false and true. False is 0. So I connect it like this. And this is the pattern I created. This is the data I want to call. So as the output, I have this first set, second set. And now let's get back to the data structure I was speaking about. Grasshopper is keeping the data structure, the addresses of all the branches, even though treated any kind of operations, any kind of component. So right now, when we just put these two data streams together, I get very nice list of data. I can use merge for that. And at the end, I get 22 branches. That means 22 columns. Each of the column has 12 values, so 12 points in the column. But it's zigzag, or the chessboard structure. Now let's get to generating the actual cards. We will generate these cards as rectangles in space. So let's use a rectangle component that says create a rectangle on a plane. I'm just thinking if this is the best way how to do it. Other way could be because when using this rectangle, we are defining it by the domain. I'm not sure if you were working with domain, so maybe
a little bit we were.
Okay, Jan is telling that yes. Okay, we can do it like this. Basically, let's explain how the rectangle components work. We have a rectangle base plane. That is basically a point in space, but not only point, it has certain orientation defined by X, Y, and Z vectors. And you are drawing the rectangle in the X and in the Y direction of this plane. But let's put it on the top view and look on it as a two-dimensional object. Defining this kind of geometry by X and Y domain scale, let's say, means that this is the, let's say, the center of our plane, which is 0, 0. And now I'm drawing a rectangle in the domain which is by default -1 to 1, and Y is -2 to 2. That means that our rectangle has scale between -1 and 1 and -2 to 2. And basically this is the rectangle we draw. So when thinking about how these inputs have to look like, we have to do these recalculations of going from the measurements that we want the rectangle sides to be 5 centimeters and 10 centimeters. We need to go into the size of domain kind of data. So let's keep this drawing over here. And let's say we want the card to be 30 centimeters wide and 60 centimeters or millimeters, doesn't matter actually, millimeters long. That means that we need to do create a domain. So construct domain that will go not between 30 and something, but we need to go between -15 to 15. So we will divide with basic mathematical operations. We will divide this number 30 by 2, create a 15, and then use the negative operation, get -15, and directly here I get 15. Okay, let's do the same with the 60, with the second measurement of the rectangle, with the y, and we have x and y. You can see here we have a sample rectangle placed not on each of the points we want to create it, but we have it on a default plane, which is xy world plane around the 0, 0 point. And you can see that the rectangle is centered around this point. Now, if we use these points as an input for the rectangle plane, we can actually transform these points with the plane component into planes, and we can use x, z plane, which is vertical. You can see it in the preview over here in the corner. And when we draw these planes over our grid and use them as the rectangle centers, we start to do the distribution of elements over the grid. Now, let's move on a little, because to have all these elements oriented in the same direction is not that interesting, and that's not something we wanted to achieve. We wanted to achieve diversity, so each of the planes should be oriented differently. That means that we need to generate different different kind of data or different measurement for each of the point of the grid. There are multiple ways how to do this. One of them is the basic tractor logic. You can inform this structure by some vector fields, or there are many concepts. You can this kind of layer on top of each other and use this way of thinking for generating the data you need. Right now we will be using the Perlin noise. As Ján mentioned in some of his lectures, Perlin noise is one of the ways how to in an easy way generate data that has some good gradients over them. So let's start with Perlin noise. And we actually need to create and generate planes, each plane for a certain rectangle. So let's have construct plane. That means construct the plane from an origin point and x and y axis. So we basically need two vectors and a center point or origin point. Center point we have already over here. That is the grid we have created. So we can use directly the output of the merge as the O input. And now we need to generate certain vectors for x and y axis of plane. Okay, Perlin noise is a mathematical function that is calculating number between -1 and 1. It has certain scale because it's a certain pattern of this is the way how to imagine it is. It's a gradient between black and white, and the scale means how the noise of this pattern is, how big is, how rapidly is it changing. So that's the S input, that's the scale coefficient, and the time means that we are randomly going through a lot of it's basically the time over here basically means that we are changing random seed of this function, but with slight change of time, the values are changing not randomly, but they are changing smoothly by the smaller the changes, the smaller of the outputs we get. So let's start with points of grid. For the time, we just need certain number. And let's see about the scale. As I remember, this Perlin noise function usually requires quite small numbers, so as a scale. So let's have a slider set on 0.08, and we will see about the numbers. Okay, we will need to generate two vectors, one for the x-axis, one for the y-axis of the plane. So let's have a vector created from x, y, z components. And we will use these numbers for the numbers we get from Perlin noise. We will use for setting the lengths of this vector in x, in y direction. And we need to do this twice because we have x and y input in the plane. So let's start like this. Let's have another Perlin noise for the y input, but to get a different number, to have the vector somehow differentiated, let's add to this number of time another number just by basic addition. Okay, and you can see that right now we are getting different outputs. So this is the first rotation. But actually, right now I'm thinking that maybe better way would be to use this Perlin noise to rotate the X and Z axis, XZ plane around certain axis. So that in that way we would need not so many. We don't need to generate so many numbers, transform them into vectors, and generate the planes. So let's do it like that. Let's keep this part of definition over here upwards, so you can get back to that when we share the definition with you. Let's copy this Perlin noise part back, and let's do the rotation. And we need to rotate an object around an axis. Object we want to rotate is the XZ plane. The axis of rotation will be many items over here. I will just unpreview all the geometries and keep only the one I have selected. So we need to rotate we will be rotating these planes around axis. We get we need to generate certain separate axis for each of the XZ plane, and I really like these planes I have over here. So I will just create another XY plane over each of the point of the grid. I will deconstruct these planes, and I will get two axes for rotation. So first rotation I want to do is to rotate this around the axis of the plane. This is the axis of the rotation. What's the problem? Oh, I need to define it as a line. Okay, when doing deconstruct plane, I get axis as a vector, but in this case, the rotation component needs the input as a line. So let's use the SDL line SDL component. That means generate the line according to starting point, the direction, and length. Starting point in our case will be point of the grid. Direction is the vector we have here, and the length is by default set to 1, which is okay in this case, and we can keep it as the default value. And the angle of rotation we need to set. Now, and we will do the rotation by remapping the numbers of or the values from the Perlin noise. As I said, the Perlin noise is as an output of a Perlin noise function, you are getting numbers between -1 and 1. And these values we can later on remap into the domain we can calculate with. By default, all the rotations, all the angular calculations in Grasshopper are made by or are counted in radians. I'm not able to do these calculations in radians very quickly, so I'm always recalculating into degrees. No, it's a different one. So I need a degrees input to transform into to radians, and I will be remapping the values of the Perlin noise, which is, I believe you have done this remapping thing in previous workshops with it was Tuesday, I think, with faculties. So I will just need to set the source domain and the output domain of the remap. So I will construct domain. Domain of Perlin noise is between -1 and 1. And the target domain should be, for now, let's say, between -45 and 45 degrees. I will use this, transform it into radians, and do it use it as an angle of rotation. Okay, so here we should have the rotated planes, but these are rotated ones. I want to do another rotation by second axis, so I will just copy this rotation over here, and I will use output of the rotation of geometry as an input for the next rotation. I want to rotate around the Z axis, and I will use this second Perlin noise for the second rotation. Okay, I get a set of planes, and I just want now to preview these rectangles we have here. And now we can basically set the orientations or set the scale of the Perlin noise function, and set the boundary values for rotations. So we are satisfied with, let's say, design part of this exercise. So let's take a look. Firstly, I don't see that much of a gradient. I think this this distribution is more or less random, so we should scale down the Perlin noise. Yeah, I will just completely change this slider, because you can see that at numbers around 0.001, I get nice results in this scale we are working on. So I will just change the maximum into 0.02. Let's say, let's try it like this. And yeah, still the resolution is not so smooth, but I can maybe add some decimals, and now we get smooth result. Okay, so this is the output. This is the distribution of scales in space. And now let's go back to this picture we have. You can see that for holding these scale elements in place, for each of the column of these elements, we used two load-bearing rods, and the opening or the cuts in these rods had to be calculated precisely, so they are defining the angle of the scale, and there was the biggest challenge of this workflow, that we need to calculate this precisely with the thickness of material. So I think for the case of this exercise, it will be best if we don't do that multiplication of that load-bearing system, but we just make a showcase with one load-bearing piece, and we will see how is the intersection calculated. So let's go actually back to the very beginning, to the grid I started with. I want to take these points and use them to define my load-bearing or scale-bearing rod. I just need to create a line somehow, and I can create the line between the first and the last point of this grid structure. For that, I can list item, and I can list item is by default selecting the 0 item. That means it's the first one, and I can, with adding the output, the parameters over here, I can select either +1 or -1 item. In this case, I need the I index input 0, and I need I -1. That means I get the last one from the list, and I can draw a line between these 2 points. I will be starting at the first, and I will be ending at the last point. So I get this line, and now I can just extrude this line vertically downwards. I think it will fit this operation. Okay, so extrude curves and surfaces along the vector. So we need to set the direction. The direction should be the unit Z, that means vertical vector, and I will be going, let's say, 20 to the negative. 20 is not enough. Yeah, I can go like this. And also, maybe the nice thing would be to scale at first to make the line a bit bigger, a bit longer, so I can I can scale it. I can scale it around the center of the line. So for that, we can do point line, point on curve. So with this, I pick the center point of each of the line. I can use it as the center of a scaling. And with scaling this by 1.1, I think I get enough of the line on both sides to perfectly fit all the scales we have here. So instead of this line, I will be using the scaled one, and I get the load bearing structure. So I have the geometry of the scales, and I have the geometry of the load-bearing pieces. To calculate this precisely, we need to work with the thickness of the material. So let's get these rectangles some thickness. That will be also done by extruding the curve. And right now it's a tricky thing that we need to extrude the curve accordingly to each of the scale. But since we are working with the parametric model, we can actually count, or we can find a way how to calculate the vector that is perpendicular to each of the piece of the scale. So that means that I'm generating rectangles around the plane that is defined over here in the rotation. So I can just deconstruct this plane, each of the plane, and I can use the Z vector, the Z direction of the plane, which is always perpendicular to the plane itself. So I'll be extruding this boundary curves by the Z direction of the plane they are constructed in. I need to give them a certain thickness. When I have a vector and I need to assign it with certain value, I can use amplitude component. Input is a vector, and I can set the length by number. I think 5 might be fine. 5 might be even too much, so let's have 2. Okay, so now we have a thickness, but it's only a frame. When we have a frame or an extrusion of some curve, which is linear, we can make a boundary object boundary representation out of it using cap components. So yeah, right now we have these elements with a thickness. And we should also give the thickness to this extruded load-bearing rod. So let's extrude it one more time. This is in perpendicular system, so I know that I will be extruding it in the X direction, and I can extrude it by the same thickness as I did with the cards. And I believe I will be having, since I was extruding the surface by extruding, I get closed B-rep. Now we need to calculate the intersections between each of the card element and the load-bearing piece. That will be done by we go to intersect grasshopper components, and we are going for physical intersections between B-reps and B-reps. I will say, because this might get kind of heavy. I will reduce number of elements here because it's not necessary to have to work on such a big data right now. This is enough. And we will be doing intersections between this geometry and this geometry. Okay, you can see that we get certain curves as an output. Now the challenge is that we need to calculate or define, because this intersection is aligned in a plane of the card element, but the piece, the card element, and also the load-bearing structure will be laser cut as a flat panel. So we always need to count with the perpendicular cuts, and we need to do a little workaround to count these or to define precisely these intersections. So we need to somehow represent what is the bounding box of this intersection in the plane that is respective to the element itself. So for that, we will be counting, or we will be using bounding box component. As an input, we will be using intersection curves. You can see that right now we have generated a bounding box that is aligned with the XY world, but we need to align this with for each of the scale separately. Fortunately, we have our planes we are working with from the beginning. So for each, bless you, for each of the element, we have an actual plane that we need to work in all the time when doing these calculations. So we use this plane as an input for bounding box orientation plane. Okay, we have some Okay, to keep the exact data structure, we need to graph in here to be working only in on a level of element. So we need to have one element on each of the branch of the data tree. So right now we have these intersections. And actually we can right now do the uniform scaling. Scale, no, non-uniform, not ununiform. And we can scale this bounding box. In these planes we are working in, but only in the Z direction, so we get longer geometries and we can do better intersections. And now I want to do the solid difference, and I want to basically subtract this object, this bounding box of the intersection from the actual card. So where do I have this data? The card is over here, right? And okay, also here I need to graft the data tree, and I can do the solid difference with these non-uniformly scaled structures. Right now, when I select just these items, you can see that we have generated the openings that have a thickness that is varying, changing according to the orientation of the card, in a way that it is the opening is always perpendicular to the object itself, to the material, and you can always fit the load-bearing part through each of these pieces. So you can see that basically from this angle I'm showing you the geometry. I can always fit that certain element I was working with inside. So let's keep just these two geometries highlighted. First one and this. Second one. Let's preview everything else. Yeah. So this is the basic logic of how we have done this prototype, this exercise. When we go over here, I will explain the differences between what I've shown you and the actual thing. We were working with two rods. What needs to be done on top of what I've done right now is we were also cutting an opening into the load-bearing part. So basically, we are not doing this full cut into the card element, but we are doing only the half of the depth, and the rest is cut into the load-bearing part. So we get the perfect orientation of the element held just by positioning it in the correct place. But the logic behind this is the same as I explained over here. And also there was another one element for each of the columns, and it was the steel rod that is that is holding all these elements in place. And again, the same process, the same principle. We were just able to fit a steel rod somewhere through. We found a place where there is a mass of each of the card, and we were just able to cut an opening through each of the card and hold it by steel rod in a place. But again, the whole process of making intersections of geometries and working with bounding box, finding the correct orientation of the bounding box in space, and doing the actual physical intersection of the bounding box and the object is the same. So I think with this you are good to go. Maybe as Ján is finishing his part of definition, I can do the same. Maybe then later on we can send you, but I think this explains enough for this. So if you have any questions or comments, just please join me or join us, and we can answer or comment.
The comment is, thank you so much.
No problem. It was a pleasure.
All good for now. Meanwhile, I have finished the definition. I just want to tell you that for me, it's always difficult to make something that has some specific result, because you need to improvise a lot. And as I told you, I'm always putting together some sort of a definition or the tutorial, so that I'm explaining certain concepts rather than giving step-by-step tutorials how to achieve something. So anyway, I did. I'm just yeah, certainly. I will share mine. I just want to show you the result. I will also send you the definition. I was just kind of too lazy to make the annotations, so in a way I will just throw you in. But I told you the logic. You see that it generated 5 legs for each of these 71 tables. It was choosing from 20 options. Those 20 options were made out of 150 different legs. So there is a lot of combinations, and I'm picking the one that is actually the most distributed one. So the connections between those legs are the longest possible. So you can have a look at this. It's not so slow. It actually calculates some time, but it's not so slow, and you can see it growing. And now I'm thinking that maybe we could 3D print this structure, because it looks like some sort of a mushroomy thing. So maybe we can have a 3D print out of this. We'll send you both of the files when we are finished. And do you have any more questions, or are you tired as much as we are already?
They commented that it's enough for now, so I think
yeah.
it's enough for everyone.
It is enough for everyone, right? Is that correct?